In Chapter 15, we study oscillations or vibrations. First, some motivation. Our galaxy is like a disk of mass, and our solar system that we're in vibrates or oscillates in and out of that disk. It's the pull of gravity which pulls our solar system back in and out of the disk. So by measuring, astronomers can measure the frequency of that vibration. And if the frequency is higher, that means the mass of the disk of our galaxy is large. So you can figure out the mass of the density actually of our galactic disk by measuring the frequency of our solar system. They use that to figure out how much dark matter, mysterious dark matter, there is within our galaxy. These are skyscrapers that are swaying during an earthquake in Japan. It's important to be able to predict the frequency that a skyscraper would vibrate at. Just like a pendulum swings back and forth with a certain frequency, so do buildings. And so it's really important to know or to be able to predict what that frequency is so that if an earthquake comes along, it's not going to cause the building to resonate and cause damage. How do you weigh an astronaut? They're weightless in space. The answer is use a spring. They hold on to this spring, as a spring here in this blue thing, and the spring is compressed and the spring pushes them outwards. They basically vibrate on the end of the spring. The more massive the astronaut is, the slower the vibration is, and you can measure quite precisely the astronaut's mass. They need to monitor their mass so their health is being kept in check. So these are all reasons why it's important to be able to study vibrations in detail. Now here's the basic example of a vibrating system. It's a mass that's hanging on a spring. Notice that the way it vibrates is it carries out a sinusoidal type of motion. Why does it do that? Why does it turn back and forth like a sine wave? The reason is because of the force produced by the spring. When the spring is compressed, it pushes out and makes it reverse. When the spring is stretched, it pulls back and makes it reverse backwards. So the spring, by the nature of the spring force, which is known as Hooke's law says that the more it's stretched, the more it pulls back. By nature of that force, that causes the motion to keep reversing back and forth and produce this sinusoidal motion. This sinusoidal motion is known as simple harmonic motion. Back in Physics 130, you learned about some of the properties of simple harmonic motion. It has an amplitude. The amplitude's the distance of the motion as measured from the equilibrium position. So our spring has a full peak-to-peak distance. That's not the amplitude. The amplitude's from the equilibrium point at the center. The period of the motion is the time of a complete cycle. So in our spring, the period is the time it takes to go out and all the way back again, completing one full cycle. That's the period of the motion. So one way to visualize simple harmonic motion is as a sinusoidal motion. But another more sophisticated and really simpler way to visualize it is in terms of circular motion. Here, the blue arrow is revolving at a steady rate. We'd say it's moving at a constant angular speed. And notice that when something revolves at a constant angular speed, its horizontal projection just traces out a sine curve. What that means is circular motion is a way to represent simple harmonic motion. This arrow that's revolving it around is called a phasor. Yes, that's where Star Trek got the name of its weapons. So we're going to use this phasor approach to be able to, in a kind of simpler way, describe this sinusoidal motion. So the radius of the circle is the amplitude of the simple harmonic motion. And the arrow, the phasor, revolves around the circle at a steady speed. So what's the angular position of the phasor? Well, I measure it from the x-axis. Remember, it's revolving around at a certain constant angular speed. Angular speed is called omega. That means I can predict the position of the phasor by taking the rate times the time. That is, omega multiplied by the time would tell me the position of the phasor at any moment. Now, the arrow, the phasor, may not start at 0 radians. It could start at some other position, so I have to include an initial angle, which we call phi. You could think of it as like theta naught. It's the starting angle. Okay, so let's put down the terms here. Omega is the angular speed that the phasor revolves at. It's radians per second. In other words, it's 2 pi multiplied by the frequency in hertz. Or it's 2 pi divided by the period, t being the time it takes to revolve around. Of course, that's also the time to do a complete vibration. Phi is the what we call the initial phase angle, and it's the starting angle of the vibration. We'll discuss that initial phase angle in a little bit. What I want to talk about now is the actual motion itself. So the position is what we care about. The phasor is a way to represent the motion, but what we actually care about is this projection of the circular motion. The projection would be given by A times cosine of the angle. So that would be A cos omega t plus phase. Notice that the maximum x position is just the radius of the circle, that's A. X max is just the A value. Okay, what about the velocity of the motion? Well, velocity is equal to dx dt. So I have to take a derivative of x to get the velocity. Derivative of cosine is minus sine, and a factor of omega pulls out. I get minus a omega sine omega t plus phase. That's the velocity. Notice the velocity vibrates. As the spring goes back and forth, the velocity is sometimes slow, like at the endpoints. At the ends of the motion, that's where it's not moving at those instants. It has no velocity there. It's going fast through the middle. So the velocity vibrates with the same omega as the motion has. Notice the velocity has an amplitude as well. There's a peak velocity that it has as it moves through the center of the motion, which is given by A times omega. Now, what about the acceleration? The vibrating mass is always accelerating as it moves. It's turning back and forth, changing its velocity. And I would get a expression for it by taking dv dt, or the second derivative of x with respect to time. So that would give me minus a omega squared times cos omega t plus the initial phase angle. The acceleration vibrates. As it goes back and forth, the velocity is changing as it moves, and there's a vibrating acceleration as well. The acceleration has a peak value. A max is equal to a times omega squared. Okay, what else can we learn from this phasor picture? Well, A is the radius of the circle. So I should be able to use Pythagorean theorem to get A squared. This is x. What about this vertical part? This vertical part would be related to sine of omega t plus phase. And so what this phasor picture tells me is that if I take, if I want a squared, I should be able to take x squared plus the vertical part squared, and that would give me the radius squared by the Pythagorean theorem. Now, what's this vertical part squared? Well, it would be related to sine. Notice the velocity is related to sine. And in fact, if I take um, v divided by omega and square that, that would be exactly what this vertical part is. So if I take x squared plus v over omega squared, that's equal to a squared. This relationship is very useful because it lets you predict what the amplitude of the motion is going to be just by knowing the position and the velocity at any moment. That may, you might then think this has to do with conservation of energy, and you'd be right, because energy conservation should be able to tell me how far out it's going to move if I know the speed it starts at and the position that it starts at. And we'll see that I get the same thing when I use energy conservation later. However, this is simply true for any kind of simple harmonic motion, whether it's a mass going back and forth on a spring or our solar system vibrating in and out of the plane of the disk of the galaxy. If you know where it is and how fast it's moving at any moment, you can predict how far out it's going to get. Notice that the acceleration is just proportional to the position. Now, why would that be true? Why would the acceleration of the mass on a spring just be proportional to the position? Let's go back to the picture of the spring to understand that. Notice that the acceleration is very large when it's turning around and being thrown back in the opposite direction. And when is it being thrown back in the opposite direction? Well, that's when it's extended the most. You see, it's all because of the force law, Hooke's law of the spring. When it's stretched out far, that's when the force is greatest and it's going to accelerate back the most. So this fact, the acceleration is just proportional to the position, is closely related to the force law of the spring. Let's now make that a little more precise. So we just saw that in general, for simple harmonic motion, whether it's a spring or whatever it is, we saw that the acceleration is just minus omega squared multiplied by the position. Check that here. You see, the acceleration is just a minus omega squared times a cosine, which is just the x value. So at any moment, the acceleration is always just minus omega squared times the position. That's a lot like Hooke's law. Hooke's law says the force of a spring is proportional to the position. In fact, Hooke's law says that force is minus k times x, which just means that the force of the spring, how hard it pulls or pushes, is proportional to the stretching of the spring. What does this mean about acceleration? Well, Hooke's law, so now if I use Newton's law, so I put Hooke's law and Newton's law together. Newton's law says the acceleration is force over mass, which would be minus k over m times x. That's just taking the force and dividing by the mass. So this is actually telling me something very important about the spring. Compare our general equation for simple harmonic motion to what we've seen from Hooke's law and Newton's law. If I put those two together, look what it does. It predicts what the value of omega must be. It's telling me the frequency of the vibration. It's telling me that omega squared must be equal to k over m. Or in other words, the value of omega is the square root of k over m. So what Newton has done here is he's now allowed us to predict the frequency of the vibration if I know the force constant of the spring and I know the mass of the thing attached to the spring. It means that we can, you see, this is how you weigh the astronaut. In that case, you're measuring omega. Actually, you probably measure the frequency f, and remember, omega is 2 pi times f. So you'd measure the frequency of the astronaut as they vibrate, and from that, figure out what their mass is. To summarize it another way, we see that the reason something vibrates is because there is a restoring force that acts on it. In other words, there's a force always trying to pull it back to its equilibrium position. That's exactly how a spring works that obeys Hooke's law. When x is large, there's a large force pulling it back towards zero. That's a restoring force. And we see that if we know the properties of that force for a spring, it means you got to know what the spring constant is. You got to know the k value. If you know how strong that restoring force is, you can actually predict how fast it will vibrate. Now let's look at some examples of figuring out the initial phase angle. The initial phase angle can be predicted by knowing the initial conditions of the motion. For example, suppose that at t equals 0, you know that the vibrating object starts at x equals 0, and it has a positive velocity. The phasor picture will be very useful here to visualize this. So how would I draw the phasor in this case? Well, it's starting at x equals 0. So that means that I have the object on the spring. It's starting at x equals 0, but I give it an initial positive velocity. Like I hit it with a hammer, so initially it moves forwards from the 0 position. That means that it will have an initial phase angle, which puts the phasor right here. And then it's going to revolve around from there at speed omega. You see, that way it's starting at x equals 0 on the x-axis, starting at x equals 0, and it will move out in the direction of positive velocity. So this means the initial phase angle is minus pi over 2. So our position function, x, is going to be a cos omega t plus the phase angle, which is minus pi over 2. This can be simplified. Cosine of omega t minus pi over 2 is just the same as sine omega t. So it's still a sinusoidal graph. It's no longer, I'm not writing it as cosine, but instead sine of omega t. These are equal to each other. They're the same thing, just a simplified way of writing it. And so that makes a lot of sense because now it's now a sine function like this. This is x of t. So at t equals 0, it's starting with a positive velocity, starting from x equals 0. What if it has a negative velocity? So it's at the initial 0 position, but I hit it backwards with the hammer at the beginning. This means the initial phase angle, the phasor initially at t equals 0, must be at positive pi over 2, right here. That way, the vibrator is starting at x equals 0, and it's initially moving backwards as it revolves. So the phase angle is plus pi over 2 in this case. That means that x is equal to a cos omega t plus pi over 2, which is exactly the same thing as minus sine omega t. That's minus a sine omega t. And if I graph that, we should look at it as a sinusoidal motion as well. Minus sine looks like this. You see it's starting from x equals 0, but with a negative velocity, hit in the negative direction initially. Suppose the initial conditions are that it starts with a negative x value, but has a positive velocity. Can we visualize that? And the question is, in which quadrant is the initial phase angle? You should pause the video and try to figure it out yourself for a moment. So I want it to start on the negative x-axis. That means it has to be either in the second or the third quadrant. But I need it to start with a positive velocity. That means it's going to be somewhere over here in the third quadrant. That way, as the arrow revolves, the arrow's here. That way, as the arrow revolves around, it's starting with a negative x position, but moving in the positive x direction initially. So the answer is it's going to be in the third quadrant. The phasor is in the third quadrant. What if it starts with a positive position and a positive velocity? Okay, so it's starting with a positive position. That means it's either in the first or the fourth quadrant, but with a positive velocity, that means the phasor starts down here in the fourth quadrant. That way, as the phasor goes around, it's moving to the right at the beginning and in the positive x side. And so it's starting it'd have to be starting in the fourth quadrant. So in these two cases, I could only just figure out which quadrant the phase angle's in. If I had actual values, like x naught's equal to -1 and the velocity v naught's equal to +2 or whatever, then I can actually figure out exactly what the initial phase angle is. How do I do that? Well, the initial position is a cosine of phi. That's found by plugging t equals 0 into the simple harmonic motion equation. The initial velocity is minus a omega sine of phi. What this means is I can solve for the initial phase angle by dividing the initial velocity and position. You see, if I divide these two equations, I will learn that tangent of phi is equal to minus v naught over omega x naught. That way, if I know the initial velocity and position, and I have to know the frequency too, then I can figure out what I can solve for the phase angle. You'd have to say that phi is equal to arctan of this fraction. For example, let's repeat one of these and see how it goes, like the first one. Suppose that x naught's equal to 0, but the initial velocity is positive. I plug that into this equation. It tells me the tangent of phi, it's equal to minus v naught. I have to divide by x naught. Well, x naught's 0, so dividing by 0 gives me minus infinity on the right side here. What is arctan of minus infinity? Minus pi over 2. Just as we argued on physical or visual grounds, figuring out here, just kind of visually figuring out what the phase angle is. Of course, this method works for arbitrary initial positions and velocities. They could be any. If you know how it starts, you can figure out what the initial phase angle is. Now let's do a couple quick examples for practice. We're given the mass of an object undergoing simple harmonic motion. It may not even be, an object on a spring. It's just something which is oscillating. we're given the acceleration and the position at a certain moment. And from that, we're supposed to figure out the time for one oscillation. The trick here is that remember that acceleration at any moment is always proportional to the position. That's a general feature of any simple harmonic motion. That when the extension is big, that's when it's accelerating back the most. There's a restoring force and all that that causes this vibration to occur. So by knowing the x value and the acceleration value, you can figure out omega. Omega is going to be the square root of minus a over x. And from that, I can figure out the value of omega, and I can figure out the period. Actually, that's what we want, is the time for one oscillation. We actually want the period, which is 2 pi divided by omega, which would be 2 pi square root of minus x over a. Which is 2.09 seconds. Next example. A glider on an air track oscillates at the end of a spring. So here we do have a spring. The motion is governed by Hooke's law. The spring constant, or they call it the force constant of the spring, 2.5 newtons per centimeter. Here we're given a graph of the acceleration of the glider as a function of time. Sometimes acceleration is easier to measure than anything else. Our phones have accelerometers built into them. So here's the acceleration versus time. And from that, we want to figure out all these things: the mass of the glider, its maximum displacement, and its maximum force that it experiences. The trick here is to remember that acceleration and position are very closely related to each other. Again, remember that the acceleration is minus omega squared times x. In this case, I'm given the graph of the acceleration. From the graph, I can read off the period of the motion. Remember, the frequency that the acceleration vibrates at is the same as the frequency that the motion itself vibrates at. So I can read off the period from the graph. It is 0.2 seconds. It means I basically know the value of omega. And if I know the value of omega, I can figure out the amplitude of the motion. In part A, I want to know the mass of the glider. Okay, well, remember that you can figure out the mass of the astronaut by measuring the frequency that they move at on the spring. And that's what we're doing here. M is equal to K times omega squared. Let me remind you, it's this. Omega is root K over M for a mass on a spring. So I made a mistake. What I meant was the mass can be predicted. The mass is K divided by omega squared. I know the period, so I should write this in terms of the period. Omega is 2 pi over the period. So this gives me K times T squared divided by 4 pi squared. The longer it takes to complete the vibrations, the bigger the mass must be that's attached to it. This is how they figure out the mass of the astronaut as well. So in this case, we plug in the period and the spring constant. Be careful with the units. You got to convert to newtons per meter, so it's all in standard units. And the mass comes out to be 0.253 kilograms. Next, what's the max displacement of the glider from equilibrium? That means the amplitude. Since I'm given the information about the acceleration, I'll use that to figure out what the maximum position is. You see, from the graph, I can tell what A max is. I can tell that A max is equal to 12 meters per second squared. On the other hand, the peak acceleration is A times omega squared. I pretty much know the value of omega from knowing the period, therefore I can find the amplitude. A, that means x max, its value comes out to be 0.0122 meters. And finally, what's the maximum force that the glider exerts, that the spring exerts on the glider? Well, that's easy, that's just Newton's law. F max must just be the mass of the glider multiplied by its acceleration. So plug in the mass, the A max that we just found, and you'll find the maximum force in newtons.